Hello there, my name is Joseph, and today I'm going to be your tutor for mathematics. And very quickly, I'm going to consider the topic trigonometric identities. So, very briefly, what are trigonometric identities? Trigonometric identities basically are mathematical statements that relates multiple trigonometric functions together, and these statements of trigonometric functions are actually very useful in solving various mathematical problems. Okay, so we are going to look very quickly at some trigonometric identities. We will try to prove some of them, and we are also going to see how those trigonometric identities help us in solving trigonometric mathematical problems that have trigonometric variables. So thank you very much, and let's jump right into it. Let us consider a right angle triangle drawn just like this. Okay. Okay, so this right angle triangle has a side which is perpendicular. It also has an angle theta embedded in it. Okay, so this side that is perpendicular is actually 90 degrees. Since this is the side facing this perpendicular angle, it makes this side of the triangle the hypotenuse. Of course, since this is my angle theta, it means this is my opposite. And the last side is my adjacent. Okay, you will also agree with me that since this is a right angle triangle, of course, by virtue of being a triangle alone, it means the sum of angles embedded in it will be 180 degrees. I mean the interior angles of this right angle triangle. Okay, so let me call this angle X, for instance. Okay, so if I call that angle X, my goal is actually to find what would be the value of X. Okay, so since it is a triangle, it means sum of angles, the sum of interior angles must be 180 degrees. So I can write theta plus X plus 90 must be 180. The implication is that X, which actually become 180 minus 90 minus theta. So I am making X subject to formula, and X will actually become 90 minus theta. Okay, so that is my value for X, and I can just replace X as 90 minus theta. Okay, so since I have been able to find my X as 90 minus theta, now let me give this right angle triangle sides. So let me call this side A, let me call this side B, and let me call this place side C. Okay, that means this hypotenuse is A. Okay, the theta, the side facing my angle theta is my opposite, and that is B. And the last side is my adjacent, and I call that side C. Okay, so for my SOHCAHTOA is actually an acronym. What it means is that sine of an angle is always opposite of a hypotenuse. Please take note, it must always be a right angle triangle. Sine of an angle is always the opposite of hypotenuse, because sine of an angle is the adjacent of hypotenuse. The tangent of any angle is the opposite of the adjacent. Okay, so from SOHCAHTOA, which is already written, I can say that sine theta, okay, my reference point is on theta, so my focus is on theta. So sine theta will actually be opposite over hypotenuse. Opposite over hypotenuse. So B over A. Cos theta is the adjacent over hypotenuse. That is C over A. Adjacent over hypotenuse. And also tan theta, opposite over adjacent. So my opposite is B. My adjacent is C. So B over C. Now, what I want to do is I want to change my reference point. I was looking at theta. So now I want to change that and focus now on 90 minus theta. Remember, SOHCAHTOA still works. The only difference is that this side becomes my opposite and this side becomes my adjacent. So since my focus now is on 90 minus theta, this is the angle I am actually looking at. So this place now becomes opposite and this place now becomes adjacent. Of course, the hypotenuse remains the same because it is the side facing 90 degrees. So what will be sine 90 minus theta? Sine 90 minus theta, remember, opposite over hypotenuse. So the opposite now is my side C, this place I call C. So it is C over hypotenuse A. Cos 90 minus theta, that will be adjacent over hypotenuse. So the adjacent this time around is B, so that will be B over A. And tan 90 minus theta will also be the opposite over adjacent. So opposite over adjacent, and that is C over B. Okay, so I've been able to get these values for theta and 90 minus theta. So what do I want to do? I want to look at the relationship that exists. Is there a relationship between theta and 90 minus theta? The answer is yes. If you notice by inspection, sin theta is actually the same value as cos 90 minus theta. You can actually see it. Sin theta is B over A, cos 90 minus theta is B over A. That is a trig identity. So you take note of that. Okay, so sin theta is equal to cos 90 minus theta. Number one. Okay. I also noticed that cos theta, C over A, is actually sin 90 minus theta. C over A. That is another trig identity. I take note of that. Cos theta is equal to sin 90 minus theta. Number two. Okay. Thirdly, I want to see, what if I divide sin theta and cos theta? Let me see what I'll get. So, sin theta divided by cos theta will actually give me sin theta is B over A divided by cos theta C over A. Okay? And that is actually equal to B over A times A over C. And of course, because they are multiplying and this is the same, they can just cancel out. So this cancels out and that gives me B over C. And you can see that this B over C is actually the value of tan theta. So that is another trig identity. So we take note of the third one. The third one being that sin theta over cos theta is always equal to tan theta. So you must also take note that this value, this trig identity is always true for any value of theta. So I've been able to prove these three trig identities. I've been able to show that sin theta is cos 90 minus theta. I've been able to show that cos theta is sin 90 minus theta. I also have been able to show that sin theta divided by cos theta is always equal to tan theta. So now we are going to see how these trig identities actually helps us in solving mathematical problems. Problem on the board. I want to see how we can employ those trig identities we've actually talked about. How can we employ them to solve these questions? Okay, so for number one, we have that given that cos theta is sin 50, cos theta equals to sin 50, obtain the value of theta. Okay, so this is quite easy. Solution, you can see, recall that sin theta is always equal to cos 90 minus theta. We've shown this. Okay, so if that is true, if I now give theta a value, like what is written here, sin 50, it means that sin 50 will actually be equal to cos 90 minus, so theta has a value now, so it will be replaced. It will no more be theta, it will be 50. So sin 50 is actually cos 40. Okay? So since we've gotten that sine 50 is actually equal to cos 40, that means instead of writing sine 50 here, I can just replace with cos 40. Okay, so the question actually now becomes cos theta is equal to cos 40. Equality holds, so I can replace. And since cos theta is cos 40, you can just say by comparing both sides of the equation that theta now becomes 40 degrees. That is okay. So for the second question, I am also employing the same trigonometric identities I have talked about. So this time around, I'm actually going to be faster. Now, I know that sine theta is cos 90 minus theta. If that is true, it means that sine 15 must be equal to cos 75, 90 minus 15. If that is true, it also means that cos 30 must actually be equal to sine 60, and it also means that cos 35 is actually equal to sine 55. Okay, so since we've been able to show this using our trig identities, we can just plug it into our question. So this becomes, instead of saying sine 15, I can replace with cos 75. So it becomes cos 75 over cos 75 plus this now becomes sine 60 over sine 60 plus 2 into bracket. So since this is equal, I can replace this. So this becomes sine 55 over sine 55 all square. And that gives me, this is 1 because numerator and denominator is the same. So it's 1 plus 1 plus 2, okay, this is also 1, 2 into bracket of 1 square. And that gives me 2 plus, so this is 2 times 1, 2, 2 square is actually 4. So this is 2 plus 4, and that ends up as 6. So we can see that those trigonometric identities are actually very useful tools in solving some trigonometric problems just like this. Okay, so thank you, and I'll meet you next time.